immediately without the coffee break. The coffee break will be later on. We will start a new section called Boundary Layer and Surface Process session, of course. The first presentation, the authors, they are not here, so we will skip it, and we will move to the next one, which is named the Could LIDAR methods automatically detect the top of the atmospheric boundary layer. Case study for Santa Maria Chuva. And this work will be presented by Henrique Barbosa, which will kindly replace the authors.
Yeah, they are not here as well, so they sent me the presentation, and so as Gilberto said, the authors are not here. Eduardo asked me to present this case, and it's a paper on they tested if cloud LIDAR methods can be used to detect the height of the boundary layer, and they took a case from Chuva, case for the last campaign in Santa Maria. You all know the place. You have seen these kind of pictures all day long. And they choose just a few days into these, into all the data sets from Chuva. And the objective of the work was to try and verify three different methods. One method which we call the gradient method, another one which is the wavelet, and the last one just calculating the height of the clouds from the Richard number using the radiosondes themselves. For the students in the audience, this is what this system looks like. It's a small cabinet. It doesn't look like from the picture, but here you have a 20 centimeters Cassegrain telescope, a laser beam that is deflected upward. And how does a LIDAR measure something in the atmosphere? It fires these laser pulses up, right? So as it reflects on a layer of particulate matter or clouds or even the molecules in the atmosphere, part of this light will be reflected backwards, and then you have a telescope connected to analogic to digital converter, photomultiplier tubes, and you are able to record the signal. If you use the LIDAR equations, you can invert and get a vertical profile. So this is not our system, but it's how it looks like. It's also operates in the green light. And so if you take the LIDAR equation and you take your raw data, so this is as a function of height, how the signal changes as you look up. And in this particular example, there is a low cloud here at 1.5 kilometers in the atmosphere. So how does the first method that they used works? If you look at the profile of aerosols in the vertical, you're going to see a layer of aerosols here near the ground. You don't see anything below a certain height just because your telescope is not looking at the laser, right? And the green line represents the molecular atmosphere, just the regular scattering, Rayleigh scattering in the atmosphere, and this is your boundary layer. You have to cut this and imagine that you have constant aerosols within the boundary layer down here. So you can look at this profile and say, look, my boundary layer goes up to here. And you can do this very easily, just computing the derivative of the signal and looking when it's most negative. That's the top of your layer. And that's what these equations and the text says. You take the correct for distance, take the logarithm, then the derivative, and you are able to determine, take the derivative and look for the minimum, and then you have the height of the boundary layer. The second method is like, oh, maybe I have multiple layers, maybe the signal is more complicated and the derivative is not enough. So they took the wave-length transform of the signal. And now they look at the minimum of the wave-length coefficients in the atmosphere. You would have to go into the papers to understand really how the method works. But it's supposed to correct part of the mistakes that you can do just looking at the derivative of the signal. Okay? And the last method is just to use the calculate theta from the radiosondes, calculate the Richards number, and look at when it gets below 0.25, when there is not enough mixing to be considered a boundary layer, then you set so this is the height at the top of the boundary layer, right? So case studies. This is an example from Chuva. I believe I just cut I was playing around with the pictures and I cut the date. But I think this is one of the first dates as soon as in the first week of the Chuva in Santa Maria. And you can see fairly easy, I hope, from the colors on this sector, that you have a boundary below 1,000 meters. So we have a very strong signal of particles around 500 meters or so. Then you have an extra layer that goes up to here. You see more dark bluish colors. Then you have clouds, right? Thanks. So what is the LiDAR seeing? So this is the range-corrected signal from the LiDAR. And if you calculate those three equations, so this is the blue curve is the first one is just the derivative of the LiDAR signal. This one is the wavelet, and just from the Richard number calculated from the profile from the radiosondes. And I tried to stretch the two pictures so that they have the same time span. And we can see that first you have a much higher time resolution, obviously, than just using the Richard number to define a height for the boundary layer from the radiosonde, because you have very few radiosondes every day. And these systems can have the same time resolution as the LiDAR, which is in this case is roughly 1.5 minutes. Over here, they agree very well. Very nice layer, easy to see. And as soon as you start to have some clouds, and the layer starts to mix up a little bit more, the gradient method gets confused. So it changes a lot from profile to profile as you try to calculate the derivative and find the minimum. And the wavelength is more stable, but depends on tuning the parameters to do the wavelength transform of the signal. Things get more complicated once you have sublayers. So you have more than one layer of particles. Both algorithms can get these wrong. So here you have a layer close to the ground, another layer, even some transport layer here, and actually the time is going to the right. But particles get more and more water, a cloud starts to form and dissipate, then you have just humidified particle over here, cloud forms later on that same day. If you compare again what both algorithms are seeing, the gradient cannot really define where the boundary layer is. So in this region, it is getting this part here, while the wavelet is getting the, let me try to point it, is getting the other, this other one over here. Okay? And when you have clouds, it's fairly easy to determine because it's just the base of the cloud, then you know where it is. So, and then both methods agree. They also tried a different case with not layers, but a more turbulent day, so there is more mixing in the vertical. And again, you can see that this is the time in UTC, so this is the part in the morning. You have some remaining from the previous day, and then you have the other layer growing down here, and they mix. So we have this mixing with what is going on later. And if you compare once again, as the new layer starts to grow and push upward what was there before, we get a similar constant height for this, for the wavelet, but not for the simplest method of them all, which is just take the derivative of the signal. As their conclusions is that both the gradient method and this wavelet transform of the signal give similar results if the atmosphere is well behaved. The wavelength method, wavelet method will get you better results when you have more complicated situations like sublayers or more mixing in the vertical. And they seem to be very reasonable. From the pictures, you can see that we're really detecting the height of the boundary layer, and it can be very helpful in diagnosing the models. And because you have a much better time resolution than just looking at the radio sound every 6 hours or so. So it's a nice data set. I think that the groups should start talking more in Chuva, like people analyzing data from one instrument with the other and try to integrate everything with the modeling component. That's, I think, the way to go for now at this stage. So thank you very much. And if you have a simple question, I can answer. Otherwise, you ask the authors themselves. And thank you very much.
Thanks, Enrique, for this very interesting presentation, because it brings a different type of equipment for the audience, and I guess that this equipment. Do you know if this equipment will move to Manaus for Go Amazon, or there is another LiDAR there?
Yeah, this one should go in principle. We could put it just on the other side of the river, for instance. We have our instrument from the Physics Institute, which is upwind. And they have a small backscatter LiDAR like this one on the Go Amazon site at Manacapuru as well. Yeah. So you're going to have at least 3 systems looking at these things during the next campaign.
And it is very interesting because, say, it's a new type of equipment, like using remote sensing to derive a very important parameter like the height of the boundary layer and so on.
Exactly. Yeah.
But any questions? Please.
You know if they use the NT3000 trying to check if
as far as I know, they have not, but I know that HIAD was looking into that. I don't know if he has submitted a different paper with this analysis for this current workshop, or he's still doing the analysis, for instance. I know that for the previous campaign, I think from Belém, or I think it was from data from Belém, for Fortaleza, we present something in a LiDAR workshop in Bolivia in 2011. A comparison between the boundary layer height measured from the LiDAR, from the MP3000, and from another instrument which I don't remember. Yeah, probably. Yeah, sure.
Your first picture,
for the first case? Yeah, okay.
Down to the cloud with the vehicle.
Yeah.
So it's raining.
Not reaching the ground. Much more common than I thought before I started to look into the LiDAR data. Happens all the time. Yeah, exactly. And it's actually humidifying these layers down here, so it's all the time. All the time.
And that's definitely just remove that detection of radar, because you can disenfog.
Yeah. Exactly. So we have to combine the instruments. None alone is going to do the job that we need them to do.
The last case you showed.
This one? Okay.
Next to yeah, there's a big difference between the Richardson evaluation of
Yeah.
the height.
It's I tried to call them this morning before giving the presentation, and what I got was they are using the radio sound for the morning period, which is 9 o'clock local time.
Which would be at the beginning of the. I wonder,
Which, yeah.
Well, there's another way to get the height of the boundary layer, which is just look at the potential temperature profile.
I don't know why they went to calculating the Richardson number below 0.25, or just looking at the radio sound at the end. You have that all the index there to compare.
So I wonder what happened.
Yeah, me too. And of course, it could be just this is in units of LiDAR profiles, and this is in time. And then told me, oh, we prepared all the pictures with the same start time and end time, but it could as well be that these correspond to this part with the cloud, right? Because this part should be these clouds up here, but I couldn't verify this in time for the presentation. Yeah. Exactly. I don't think I have a profile here that will give me. Yeah, you have to decide if it's here, if it's here. So you have to, while you're doing the analysis, you have to look at the heights and more or less what you expect to be, and figure out if it could be a cloud on top of the boundary layer, or if it's a different layer of clouds. Just to not get confused. But from the simple derivative, you cannot distinguish that. You have to look into more details that you know how the atmosphere works, otherwise you cannot distinguish them. Apparently, yes. I didn't do the work myself, so I didn't really know the details, how they perform the wavelet transforms, but apparently it's filtering better than just looking at the derivative of the signal.
On that last point, if you have the LiDAR, you have a signature of the cloud and the LiDAR up to the signal piece of the cloud.
Yeah. Exactly. Yeah. The case with this with a cloud is really clear, like this one. Let me get this one larger, but it's
You have everything you need to make it.
exactly. So once you have a cloud, the signal really, really drops. So this is a very thin cloud, so I can still see some signal, but most typically low-level clouds will just kill your signal. You are not able to see through a couple hundred meters inside the cloud, at most. So.
Okay, thanks. Thanks, Henrique.
You're welcome.
There are a lot of questions about this interesting presentation.